Thanks for the intro. Here I'm going to mainly focus on sharing some of our experiences through 2 years working with Spark on analyzing machine data. So as a quick outline, I'll first provide some idea of kind of the nature of the data that we collect from our users' environments, and then go through more or less 3 kind of tips or lessons we have learned either through scaling our system for analytics or how we use Spark, its API, to program our analytics functions. So most of our target users, they run a kind of a private cloud setting using one of the many virtualization technologies, such as VMware's vSphere or Microsoft Hyper-V. So in this setting, the Hypervisor provides abstractions of compute, network, storage resources as kind of resource pools that are shared by many virtual machines and applications running on those virtual machines. And in most of the cases, these applications are not really developed as kind of a cloud-native applications. They still assume a stable runtime environment consisting of, well, guest operating systems and stable storage resources. So it's kind of, but to improve resource utilization and sharing, the Hypervisor do provide capabilities such as live migration of virtual machines to balance the load, for example, across many physical servers in a machine cluster, and also in terms of moving the storage, the data storage for an application across different storage arrays, for example. Now, because of the increased sharing of common resources, when there is an issue such as, well, an app crashed or a virtual machine is suffering resource contention due to like I/O contention on the backend array, the increased level of abstraction in the system stack do pose a larger challenge in terms of both to administrators when they need to, say, provision new applications or virtual machines for their users, and also for us in terms of having more variables in our analysis to tackle the potential issues. Now, our setup of the whole service roughly starts with, well, we provide our end users with a small virtual machine that serves as a data collection engine that uses our end users' management server API to collect data. We call generically these data sources. They could be, for example, VMware's vCenter management server or Microsoft System Center server. And then all the data that's collected gets uploaded to our backend, which we run using Amazon's cloud service. And then we provide a common platform that provides data persistence and access APIs, and all the different analytics modules are built on top of this platform. The kind of analysis we provide includes infrastructure planning, health checks, dynamic benchmarking, for example, for our users to know like the level of system utilization in their environment. How does it compare to the rest of our users? So in terms of the volume of data that we collect, right now, even with a still growing user set, we are getting over 100 billion data points per day, including both performance metrics, configuration data, task events that captures changes in our users' environment. Plus the platform that we are currently still keep building on top of Spark. Our ideal is to provide not just visibility of all the data that we collect, but also actionable insights that our user can use to optimize their environment. Now, So for the rest of the talk, we'll focus on the platform part of how we use Spark and the associated technologies to create the data persistence and access and the scalable analytics platform. Now, so if I may borrow the framing of a famous computer science textbook, all the components that I have shown in the previous slides are really about how do we understand the structure of machine data that we collect, and how do we interpret in terms of finding meaning of the data that we can provide to our end users as insights to manage their operations. So the kind of very high-level conceptual data model that we arrived at is essentially we have a set of objects. They can be virtual machines, physical servers, data storage devices with various kinds of properties. For example, they can have a name for a physical server. They can have the model of their CPU, how many sockets, how many cores they have, memory size, etc. And we have observations of these properties over time. So if we go through the kind of the three outlined boxes from the top to bottom, the top box are really about data that tells us, well, what resources are there in our users' environments? Well, how many physical servers, their model, what kind of CPU they have, etc. And then the middle box tells us about how these resources are being utilized in terms of their CPU utilization percentage, or or for, say, storage devices, what's the average latency that a user's virtual machine is observing. And then the bottom part tells about what changes are happening in users' environments. These changes can be either initiated by, say, a system administrator that powers on a particular virtual machine, or by some automated management processes. In this case, say, VMware's distributed resource manager that may automatically perform live migration of virtual machines across different host physical servers to balance their load. So we started using Spark to build our analytics platform almost 2 years ago. For us, it's a fairly quick ramp up. Our team developed most of the backend components using Scala and the Play framework for all the web services components. So we among all the team members at the time, we have about a couple years of experience programming in Scala. And also our initial usage of Spark is fairly straightforward. To me, I started with a mental model of, using Spark as Scala's parallel collection on steroids instead of running on a single machine, but with Spark, similar programming model, but runs on a cluster that you can scale out easily. Now, some of the initial analysis that we have done includes, as VMware or Microsoft releases their new hypervisor versions, we can look at the trends from our users' data, how quickly users are adopting each of the new releases. And also, we can look at in the storage devices that are present in our users' environment, what percentages are storage area networks versus networked file system, etc. Now, an initial lesson that we have learned is for our particular workload, we have to keep an eye out on the skew in partition size or the size of the RDD elements. So, for example, some of our map or flat map functions, the elements of the input RDD, they are pretty much homogeneous. For example, the input element could be a task description of analyzing the performance data of a particular data source. It's essentially consists the identity of the data source, some kind of a GUID, and let's say the starting time of a day. But then once you map this element to all the, let's say, all the available performance metrics from this user environment, then depending on the size of a user's environment, that can vary by like over 100x between, well, small lab setups to, well, large-scale production environments. So it may result in either different partitions or different elements in the RDD, their size or the kind of the amount of work for further map, etc. Phases to vary by orders of magnitude. So, but in most cases, actually, Spark's task scheduler actually yields roughly even load distribution among all the workers, as long as you have a sufficient number of these individual tasks or elements to keep them busy for a fairly long time. But we do need to use occasional repartition to resolve extreme skews that may cause some workers running out of memory in our setup. Now, for our analysis, the largest volume of data that we collect are performance metrics that provide us information about latency of any resource requests, like allocating a memory page, performing some I/O requests, etc. Now, with the kind of environments that we collect data from, there are actually two factors that boosts the volume of data in this particular category. For example, with running, let's say, dozens of virtual machines on the physical server, now previously, let's say you have 100 counters per physical server. If you are running a dozen virtual machines, that immediately gives you, well, a dozen more multiplied by 100 performance counters per physical server that you can collect from. Similarly for using multiple containers running in the same operating system. Another part is now with virtual machine virtualization technology, the compute network storage resources presented to the virtual machines are software defined, using a hot terminology here. Then that actually provides a lot more performance counters for visibility to this kind of technology stack. For example, in a recent release of VMware's Hypervisor, for a virtual machine, there are over 60 memory-related counters alone that we can collect from to analyze, well, how the guest operating system are using the memory and how the hypervisor are adjusting, say, reclaiming unused memory from guest operating systems, et cetera, et cetera. So to be able to handle such a volume of incoming data, we actually evaluated quite a few well-known open source time series database technologies, including OpenTSDB, that's our first kind of production use, and then one of its derivatives, KairosDB, and also a more recent one, InfluxDB. Now, it turns out with the default setup, even with some of the optimizations that we applied on top of those, given the volume of data that we need to handle, it's really not economical in terms of, well, how many instances we will need to run in Amazon to provide enough throughput for the incoming volume of data. So what let's say, as a quick sketch of an example, let's say we want to use Amazon's DynamoDB service to be able to handle 100 billion data points per day. It's kind of roughly on the order of our current data incoming volume. Now, from Amazon's recent pricing page on their US East region, to reserve write throughput, it costs about 0.65 cents per hour for 10 writes per second. It sounds reasonable. But once you dig into it, 100 billion data points per day translates into over 1 million per second. That translates into a per hour cost of over $700 or over $500,000 per month. And this is even before we buy some read throughput to avoid that being a write-only storage. So as we research various similar solutions of how other users are dealing with similar issues, what we ended up with is, well, we do need to have some in-memory caching layer as the input, as the data collected are coming in, and basically batch the write to amortize the cost of one write to the underlying key value store across many data points. So here are some recent blog posts that from SignalFX or MyPar of how they achieved a very high throughput in terms of persisting time series data and for efficient access. And in the end, we arrived at very similar solutions. Now, so besides the data persistence that we covered earlier, the way we organized our analysis API and how we build analytic functions is really following the philosophy of the Lambda architecture, where at a very high level, a query against a large data set is simply defined as a function applied over the data set. Now, in this case, what I'm illustrating here is, let's say, I want to provide our end users a kind of a baseline comparison capability. The middle of the timeline represents some change, for example, like a hypervisor version upgrade, etc. Then we want to compare the before and after over a certain time interval. What's the system resource utilization levels? Then in this case, as long as we define our function as being able to apply to a particular source of data over an arbitrary time range, then we can easily apply the same function across two time ranges before and after the change and compare it to see whether there is any abnormal increase in resource utilization while running the same workload as far as applications are concerned. So then in our case, because of the diversity in the machine data we collect, we do need to provide analytic programmers to be able to apply functions to many kinds of data. In this case, I'm illustrating the four categories of kind of more or less static kind of data that tells what resources are there. The relationships between different objects, which virtual machines runs on which physical servers, and uses which storage arrays for their data. Time series and events that captures changes in the environment. So what we ended up with is, if you go back, all the data elements in these RDDs are keyed by kind of a key structure that depends on the particular types of data. In the end, what we found out is, well, we are actually tackling one of the hard issues in computer science. It's really naming the data elements that we have. So in our case, the data key consists, well, the identity of the object, virtual machine, physical server, and then the kind of attribute, different names of properties, associations from virtual machines to hosts to physical servers, etc. And then the time range of this particular data element. Now, when we need to apply a function that actually gathers a subset of these RDD elements, what we came up with is actually there's a very natural naming of the particular function application in terms of, well, I'm applying a particular analysis function, say, on a virtual machine or a data storage device. Let's say this function name is whether there's any resource contention on this virtual machine. And then I want to analyze for the last week as the time range. Then we can use the data dependencies for this function to map each data RDD from keyed by the name of the data to the function application key, and then we can join the different data RDDs by this function application key, and then the resulting value in the join will have all the relevant pieces of data that needs to feed into the particular function application. So right now, this still feels a little convoluted, but they do give us a systematic way to structure our analytics workflow, both in terms of batch analysis and streaming. So in terms of our current production usage, we have kind of hourly or daily batch jobs in production since for almost a year. And we are actively developing the Spark streaming-based pipeline, which we are testing in our staging environment right now, and hopefully put in production later in the month. So yeah, so that's all we have. So any questions? And for feedback, please reach out to xj@cloudphysics.com.
Awesome. So if anyone has any questions, I can walk around.
So for your time series database,
yeah,
is Cassandra?
Right now, I think the scheme that we developed for storing the time series database using a key value like structure, our schema can actually work against most generic key value store. Right now, we are using HBase in the backend.
Very cool. Very impressive. Thank you.
Okay, thank you.
Cool. Well, awesome. Thanks, you guys. Maybe you can join me in thanking Xiaojun.